Welcome, ChemComm. Today, as we continue on in our introduction to chemistry, we're going to take a look at scientific measurement and why it needs to be standardized. We'll also take a look at how you can manipulate different measurements to fit the scale of what you're measuring. Let's get started. So let's start with why it's important that we standardize measurement. Let's suppose that you went into the hospital and you had the need to be sedated or you went under some anesthesia, and the doctor asked the anesthesiologist, hey, can I get 1 syringe of propofol? On the surface, that doesn't look like a problem, but if the anesthesiologist would show up and look like this, you could see that a syringe is not a standard measure. Syringes could be any size, so just asking for a syringe doesn't really make it clear to both the doctor and the anesthesiologist what you're talking about. So to combat this, in science, we use standard measures to make sure that everyone's talking a common language when it comes to measurement. So for instance, 200 milligrams. These measurements are based off the metric system. The metric system is divided into 2 main groups of types of units, which would be the base units and the derived units. You may have heard of these before. There are only 7 base units. That means there's only 7 very basic things that we can measure about anything. Time, length, mass, amount of a substance, which is measured in moles, which we'll talk about in chemistry because it's very chemistry oriented, temperature, and then current and luminous intensity. That's more for physics class, but those first 5 we will definitely be dealing with here in chemistry class. And you can see here also the units that they're measured in the SI system, the metric system. The metric system is basically the system that is agreed upon across the entire globe to use in the scientific community. Now there's other units that we use here in the US, like gallons and inches and feet, that aren't in the metric system, but they're a part of our culture, and it's been kind of difficult to move past those into the metric system. Here's another chart where you can see the SI base units and their symbol they're used for measurement. So you might be thinking, Mr. Hess, there's a lot more than we can measure than just those 7 things. There's things like pressure and volume and area. So what those units are derived units. And something that is derived is a mathematical combination of the base units. So for instance, if we think about volume, length times width times height, we are taking 3 base units, lengths, and we're multiplying together to get, in this case, meters squared, or meters cubed, excuse me. So that shows that we have a mathematical relationship between those lengths. Area, velocity, density, pressure, there are an abundance of derived units. If you look here, these are all derived units that you could measure in chemistry or physics. You'll notice this is how we combine the base units to get to that expression or get to that derived unit. But you'll also notice that a lot of times what we'll do is choose a placeholder symbol to stand for that rather than putting all the base units multiplied and divided together. So for instance, if you look at force, which you studied in physical science, and a Newton, it's kilograms per meters per second squared. It's the acceleration of a mass body. So you could write that out, kilograms per meters per second squared, or you could just call it a Newton, which is the placeholder that we've given the units for force. In this class, there are some derived units that we use quite a bit. Volume is one, and density is one. So it is important that you can calculate those 2 things using a couple different methods. So let's talk about that. Density is how much matter is in an object of a specific volume. The more matter is in a given volume, the more dense that it is. So for instance, mercury is a very dense liquid because there's lots of mass in a tight space, right? And that's why mercury will sink. It's a liquid metal. Something like wood is not as dense. There's not as much matter per volume, and therefore typically most woods will float on water, which has a density of 1. So to calculate density, all you do is take the mass of that substance, divide by the volume, and it gives you a ratio of mass to volume. If the object is a cube, all you have to do is take length times width times height, or if it's a rectangular prism. But most of the time in chemistry and physics, we have irregularly shaped objects. And typically how we find volume is the water displacement method. We'll take a graduated cylinder, let's say a 100 milliliter graduated cylinder, and we'll fill it up to exactly 50 milliliters of water. And then we'll put the object in the graduated cylinder and see how high the water rises. The distance that it rises would then tell us how much space that object is taking up, and therefore tell us the volume of that object. It's a very helpful procedure called water displacement, and we will use it when we get to the density lab. So let's use that formula to solve a couple of these problems. The first one here, it says, what is the volume of a sample that has a mass of 20 grams, so this is M, and a density of 4 grams per milliliter, so this is D. So if we remember, D equals mass times volume, so 4 equals mass times volume. So at this point, we have a volume variable that's in the denominator, and we need to get it in the numerator. So depending on your math teacher, you could have gone through this a couple different ways. You could cross multiply, or the same thing, you could multiply each side by V. And what that'll give you is 4V equals 20. Now we can divide both sides by 4 and see that V is going to equal 5, and that should be, it's a volume, so that's milliliters, and I get that from my density that was in grams per milliliter. So if we look at the cleaned up version here, you can see the math working out. Here's another example. It says a piece of metal with a mass of 147 grams is placed in 50 milliliter graduated cylinder. The water level rises from 20 to 41 milliliters. So this is where the water displacement method comes in. You got to kind of think about what's going on. The volume of the object is not 41 milliliters. It's also not 20 milliliters. There's 20 milliliters of water, and the water and the object combined are 41. So that means we need to subtract 41 minus 20, which gives us the object's volume, which is 21 milliliters. Now we can plug that into our density equation. And if we do that, we have 147 grams as our mass. We have the 21 as our volume of just the object. We divide and we get 7 grams per milliliter. Another important thing to talk about when we're dealing with measurement is scientific notation. In chemistry, we deal with very large numbers when we talk about counting atoms or counting molecules. So you need to be able to convert from and to scientific notation. The most important thing to remember is that your M factor must be between 1 and 10, and that every time you move the decimal, that's going to adjust the scientific notation by a power of 10. Let's do a couple examples here so we can refresh our brains on scientific notation. If we look at this 700 meters, we need to move this decimal 2 spaces to the right to get this to be 7.0. 7.0 is between 1 and 10, so that's what proper scientific notation would need this to be in. So the next question is, how many powers of 10 did we change 700 to get to 7? The answer is 2. We moved 2 decimal places, which means there were 2 powers of 10 that were used. Now, you might be thinking, well, I remember there being positive 2 and negative 2. 700 is a big number, so the exponent's positive. That's the easiest way that I can tell you to remember it. So like if you look down here to see, if you look ahead a little bit, you can see that's a really small number. Before we even do this problem, you're going to know your exponent should be negative because we're dealing with something that's very, very small. Let's look at letter B. We're moving 1, 2, 3, 4, 5, 6, 7, 8, 9 powers of 10. So this would be 5 times 10, and this is a large number, and to the 9th power. Moving along here, 1, 2, 3, 4. So this would be 2.3 because that number is between 1 and 10, times 10. And it moved 4 powers of 10, but it moved the other direction, so therefore it would be negative 4. Letter D, 1, 2, 3, 4, 5, 6, 7 would get us to 8.0, and we moved it negative 7 powers of 10. You also need to be able to go the other way if I give you scientific notation and taking it out of scientific notation. So this is positive 5. What that means is this number is a large number, which means our decimal needs to go this way, 1, 2, 3, 4, 5 decimal places. So 2, 4, and then 4 zeros afterwards, because the first decimal was the 4 that we jumped. So 240,000. If we look at F, this is a negative exponent, so that means it's going to get smaller. So 1, 2, 3. We should have 2 zeros in front of the 1, 7, 3, and 0. In G, we have 7 powers of 10. The first 2 are going to be the 7 and the 8, which means after we put the 2, the 7, and the 8, we're going to need 5 zeros after that. We get 27,800,000. And that's a review of scientific notation. So the most important thing in this class is not only understanding scientific notation, but you need to be able to do math with it. And the best way to do that is to use something on your calculator called the EE button. It tells your calculator, hey, I'm using scientific notation. The calculator therefore knows the correct order of operations. So if you look here, scientific notation of 3.4 times 10 to the second would just be 3.4, and then we'd hit the EE button, and then we'd put 2, which is the exponent. You don't need to exponent the 2. The EE is basically doing times 10 to the something. And it's doing all those within that button push. And so it saves you some time, and it also makes sure that you do the correct order of operations. Notice here, 4.5 times 10 to the 34, and we got 4.5, hit the E button, and then just 34 because that's the exponent. So let's try to use that button a few times here. So when we're adding and subtracting, if you were going to do these by hand, you'd need to make sure that the exponents were the same. So for instance, in this first one, these are both times 10 to the 6, which means I can just add together these m factors and put it at 6.5 times 10 and to the 6th. The exponent would stay the same. Now you can check that by plugging that into your calculator. And you'd put 5.2, hit the EE button, then hit 6, plus 1.3, EE button, and then hit 6. We do the same thing when we're subtracting. 8.14 minus 6.01. Since these are both 10 to the 9th, this is pretty simple. It would just be 2.13 times 10 to the 9th. Once again, you could do that on your calculator. The calculator becomes really useful in this last example here. And the reason is because these two numbers do not have the same exponent. And so what that means is I could try to convert these, or if I just use my calculator, 1.2 E3, 1.2 EE4, the calculator will do the math for me, do the conversion for me so that it can be added together. And you would get 1.32 times 10 to the 4th. When you're multiplying with scientific notation, typically you're going to add exponents together. And then when you're dividing, you're going to subtract exponents from one another. This is another time when your calculator can become very helpful. So, in this first one, we do 6 times 1 and get 6. And then we would add these exponents together and make this times 10 to the 9th. You can also use the EE button. 6 EE3 times 1 EE6, and you should get 6 times 10 to the 9th. With this one down here at the bottom, if you're not great at adding together negative numbers, it would be another chance to use that EE button to make sure. And you would get 4.92 times 10 to the negative 6th. Division is similar but a little different. We divide the numbers. 8 divided by 4 is 2. And then we subtract the exponents. So 6 minus 4 would be 2, and that would be our number. 9 divided by 3 is 3. 3 minus negative 3. Got to be careful here. 3 minus a negative 3 equal, which means this would be plus, so that's a 6. So this would be times 10 to the 6th. That's another one that can be a little tricky, and the calculator, as long as you're using the EE button correctly, can be very helpful for you. The last thing we want to talk about here is how the metric system can be very helpful because it has prefixes that are powers of 10 to increase the scale or decrease the scale of the measurement. You're familiar with this. You know what a meter is. And then like a kilometer, you know, is a much larger unit of measure. And then a millimeter, you know, is a much smaller unit of measure. Well, kilo and milli, they're just prefixes that are changing the scale by a factor of 10 away from meter. If you look at this scale, this just goes from kilo to milli. And you can see how when we go from the base unit to deca to hecta to kilo, we're increasing by a power of 10 every time. And as we go from the base unit to deci, centi, and milli, we're decreasing by a power of 10 every time. These prefixes go very, very far, and we don't use them though. But the thing that's probably most relatable to you is you know what a terabyte is and a gigabyte are because of the time you live in. Like when I was a kid, a gigabyte wasn't really a thing yet. We were still dealing with like megabytes on our computers and things. And then as more and more data, more and more HD video and things like that, we got more and more information that we needed to store on our iPods. I know that's not your generation, and our phones and our computers. So you have things on your computer, maybe HD videos that might be a gigabyte if they're pretty long. And you probably have a computer at home that has a terabyte hard drive, which is a large unit of measure for information. A petabyte is like how Google would measure how much information goes through their servers every day. But you can see it goes even farther than that. And we even have things that are even very, very small. Okay, 10 to the negative 24th. So you're not going to be responsible for all these prefixes. The ones that you're going to be responsible for are all the way up to giga and then all the way down to about nano. If you're trying to wrap your head around how large some of these measurements are, 1 petabyte of information is 13.3 years of HD video. That's a lot. That's like if we HD videoed your life for the first 13.3 years, it would be 1 petabyte of storage. If we take 10 billion photos on Facebook, that's 1.5 petabytes. And then Google processes 20 petabytes every day. And then the entire written works of mankind would be 50 petabytes. So tons of information. I don't know if we're ever going to get to the place where a home computer will hold a petabyte of information. I don't know if we'll need that, especially with cloud storage right now, but it is kind of interesting to think about. One way to remember the metric prefixes is King Henry died by drinking chocolate milk. It's just a mechanism for remembered kilo, hecta, deca, base, deci, centi, milli. The thing is, you don't have to memorize that. If you look at your equation sheet, we provide you from giga all the way to nano. And actually, this is angstroms, which would be another small unit of measure used just for length. But we provide this for you. All you have to be able to do is use it. So let's do some example problems. All right, the first one we're going to do here is go from centimeters to kilometers. So we're going from right here, centimeters, and we need to get to here. So the first thing we want to do is to decide how many powers of 10 we're changing. 1, 2, 3, 4, 5 powers of 10. Which means we need to move the decimal 5 powers of 10 in the same direction. So here's my decimal. 1, 2, 3, 4, 5. Okay, now there were some powers of 10 there that didn't have digits. Those would just become zeros. So 0.0000244. 2.44 centimeters equals 0.0000244 kilometers. Let's try another one. We're starting in grams. Grams is a base unit. Anytime you have a unit by itself, grams, liters, or meters, that will be on the base. We're going to mg, that's milligrams. 1, 2, 3. So we moved the decimal 3 to the right. So we need to move the decimal 1, 2, 3 to the right in our number, and this would be 3,570 milligrams. I'm going to skip over a couple here for the sake of time, but if you look here, we're going from milligrams, that's here, to angstroms, that's here. These dots in between angstroms and milligrams are powers of 10 that we need to count. So you can't just go 1, 2, that's not correct. Because from milli to micro, there's 3 powers of 10 there. That's why the dots are there. So 1, 2, 3, 4, 5, 6, 7. And we need to move 1, 2, 3, 4, 5, 6, 7. So a 1, a 2, a 3, and then 4 zeros would be how many angstroms that many milligrams is. With everything that we covered today, specifically with scientific notation and the metric prefixes, you're going to need practice. It's going to take a little while, even if you've had this before, to kind of refresh your brain on this stuff. Work through it, ask me questions, stay diligent, you'll be fine. Good job today. We will see you soon.